It's 10 o'clock at night. You've spent the whole day working on your visualization, and you're finally ready to click the render button. But you know it'll take a while to get an image, so rather than staying up and waiting for it, you decide that you'll check on it in the morning. So the next day you get up, you take a look at your laptop, and you see that your visualization is 1% complete. Do you let it run for the next 100 days? Or do you go out and buy a faster, more powerful computer? What do you do? Running out of computational resources is a common problem that can lead to lag, crashes, and long render times. Thankfully, there are many different ways to tackle problems like these with optimization. Optimization can be used to improve your use of computational resources to be more efficient. It can help manage your RAM, which may be the reason your software is crashing. If your software isn't crashing but is laggy and difficult to work with, you can optimize a specific version of your dataset just for faster interaction. Visualization designers often optimize their data in two different ways: a high-quality version for the render and a lower-quality version for faster interaction. Optimization can help reduce your data file size, which is especially important if you're working with big data or you're running out of stored memory on your computer. Optimization can also help speed up your render times. Oftentimes, you'll want to decide how long you want to wait for a render and then optimize until you hit that target. There's a joke in computer graphics studios that goes like this. A studio executive asks her lead artist, "How long do your renders take?" The artist replies, 20 minutes. The executive then says, "What if we were to buy you 100 of the fastest, most powerful, most cutting-edge computers on the market?" The artist replies, 20 minutes. It's not a haha kind of joke, but the point is the perfect image can take forever to render. But if you only have 20 minutes to spare, make the rendering the best that you can with the time you have. There are different categories of optimization techniques that you can use to get these results. You can choose to optimize your input data, your design, or both. Optimizing your input data will help you manage your RAM, scene interactivity, file size, and render time. And optimizing your design will further help you manage RAM and render time. The first method of optimizing your input data that you might want to try is called subsampling. Subsampling involves reducing data evenly throughout each one of your data files. Let's say this represents one data file, and each piece of serial represents a data value. We can decrease the file size by deleting every other point in this dataset. First we go in the x-axis, and then we go along the y-axis. If we had a z-axis, which would probably go in the up direction, we would delete along that axis as well if this was 3D data. We started out with a 4x4 grid, and we reduced it to a 2x2 grid. That's 75% savings in file size. It's important to subsample your data evenly so that you get a good representation of the entire dataset. Here is an example point cloud dataset loaded into the software Houdini. If we were to delete every other point of this dataset like we just did with our serial example, the data would look like this. Since this is a lot more data than we had originally with our serial, rather than deleting every other point, we might decide to only keep every 10th point. And that would look like this. But there's no reason to subsample our data in such a structured way. Instead, we might choose to delete 75% of the data randomly. That would look like this. As I move this slider, the software is taking a different random sample of the dataset. Subsampling is one of the best ways of getting a first look at your data, especially if your data is too big to load into your software, or if you can load it into your software if it's too big to work with interactively. Here we see an example of a subsampled version of a dataset alongside the final visualization. You can see that the subsampled version gives you a rough idea of what the whole dataset looks like, giving you just enough detail to make further design decisions, like selecting a good camera position. Unfortunately, we can lose a lot of potentially important data along the way. Subsampling is an easy way to reduce your file size, but we're not being very intentional about selecting which points to delete. In this example, if we were to move every other point of the dataset, the smile would be preserved, but we would lose some very important data, a nose, and an eye, which are important features in this dataset of a smiley face. Thresholding is a smarter way to reduce the file size of your data once you already know some details about your dataset. Thresholding involves deleting data that's less than, greater than, or between some specified range of values. In this example dataset, say we're only interested in the warm colors, red, yellow, and orange, and we're not interested in the cool colors, green, blue, and purple. With thresholding, we can simply do this. This reduces our file size in a much more meaningful way. One common use of thresholding is deleting values that are close to 0 or close to the low end of your dataset. Let's take a closer look at the data behind this visualization of a coronal mass ejection on the surface of the Sun. We need to know a little bit about our data before we can start thresholding. We happen to know that space is cold and that the Sun is hot, so temperature seems like a good variable to take a first look at. Here's what that data looks like as particles in the software Houdini. It doesn't look very interesting yet, because we're wasting a lot of particles on the empty cold space surrounding the coronal mass ejection. As I move this slider in the software, I'm thresholding away the colder values and leaving us with this much more interesting shape of the actual coronal mass ejection. This is reducing our file size, as well as creating this much more interesting shape. Another class of optimization methods you can use that doesn't involve touching your input data is optimizing the design of your scene and of your rendered image. One of the simplest changes you can make is changing your image resolution. An HD image, like the size of this video, will take much longer to render than a smaller image. You might want to render at a lower resolution while you're developing your visualization, and render it at a higher resolution when you're ready to produce your final images. If you don't have flexibility regarding your image size, it's important to note that lighting can be very computationally expensive. Objects in a virtual scene get their color from virtual lights. Without these lights, everything would come out dark, and your render would be completely black. To make a rendering, the computer follows virtual light rays through the scene. The more lights there are in the scene, the longer this process will take and the slower your render will be. Be smart about where you place your lights so that you only have as many as you need. Using a simpler lighting setup can help speed up your render. The material properties of the objects in your scene will affect your render time as well. Objects that are translucent, reflective, or refractive will take much longer to render than objects that are opaque. Think about how long it would take for a ray to bounce between two mirrors that are facing each other. Theoretically, this ray could be trapped bouncing back and forth forever. It would be impractical for a computer to calculate all of the zillions of possible light rays that come out of a light source. So what renderers actually do is they estimate the lighting of a scene using a smaller selection of all of the possible light rays. Sampling is a general technique across many fields of letting a portion represent a larger whole. Earlier, we learned about subsampling, which is a method of getting a more manageable number of data points. Here, in terms of rendering, sampling refers to getting a more manageable number of light rays to calculate your image. Many pieces of software have lots of settings related to sampling because it's the most straightforward way to trade visual quality for render time. You can speed up your render by choosing to use fewer light rays to represent reflections or translucency, or simply choosing to represent fewer light rays throughout your whole image. If you sample too few rays, you'll start seeing digital noise in your image. This is an especially drastic example, but you're going to have to decide how much image quality are you willing to lose for faster render speed. Multiple optimization methods can be used simultaneously, and you're likely to mix and match some of these methods while working on your visualization. And one optimization methods can have benefits across multiple computational resources. For example, decreasing file size by subsampling will decrease the amount of stored memory that your data takes, but will also reduce the amount of temporary memory that your data is using when it's loaded into your software. And it will speed up your render time because there is less data to render. There are trade-offs to each of these optimization methods. You may be losing data or losing image quality. Do you want to wait 24 hours for a high-resolution, high-quality image? Or 5 minutes for a low-resolution, medium-quality image? There's no right answer. The choice is up to you. But now, you should be equipped to start thinking about how to balance those options. Fun fact: video game designers have to be experts at optimization. Games need to render in what is called real time, which often means rendering 30 frames per second or even more. Real-time rendering is a field of computer graphics that uses many advanced tricks and techniques, many more than we learned about today. Often, these techniques are specific to the game or the visualization being rendered.